Okay, hello everybody. I'm going to talk about Cumulus. So Sergey talked a little bit about that already. It's a project we first kicked off in the beginning of the year, so I think February or March. Most of the work so far has been more like infrastructure work in the Substrate repo and the Polkadot repos as well, because Cumulus really just sits on the surface. It's at the top. It's designed with Polkadot in mind. So, we're building this thing called Polkadot. I know this is a Substrate conference, but the idea of Polkadot is that you have many different parachains talking to each other, who are all sort of agreed upon by the same consensus algorithm. We started building that project a couple of years ago. There's a lot that goes into just building sort of the core layer of this, but our plan was never to just sort of put out Polkadot and say, okay, parachain developers, you're gonna have to figure out the rest. Like, you're gonna have to figure out how to write your parachain, how to make it validatable, how to actually submit those blocks to the network. So Substrate is a big part of making parachain development actually feasible. Cumulus is the link between Substrate and Polkadot. So first, I think I'd talk about what blockchains are composed of. So we usually, so for Substrate, we started to make this distinction, which was we have the consensus algorithm. How do we agree on which chain of blocks was valid, right? Like, just what data was in there, what do we follow? One of the issues with consensus is not the problem of creating a valid history, but everybody to agree on the same valid history. This is a bit separated from the actual incentive mechanism that's underlying the consensus algorithm. So consensus just kind of assumes, like, let's say you have honest majority or something like that. It'll assume, given that presupposition, that you can achieve consensus and everybody can agree. The incentive layer, like proof of work and proof of stake, how you're actually paying those actors to, become honest, to unify the rational and honest actors, sort of a different story. And I think one other way that you can start to break down the consensus question into certain subcategories that is fairly important for Cumulus in particular is the notion of safety versus liveness. So safety is the property that you will not agree on conflicting things. Whereas liveness is the property that you will eventually agree on something new, so that the chain continues to grow. The other side of a blockchain is the state machine stuff. So state machines are basically what you're building as runtimes in Substrate. It's what is the actual logic of your chain. And if you talk to many teams who are starting to build blockchains, the main innovations that they're making are on the state machine layer, because this is where you can do all the really interesting stuff that brings new options to users. The consensus stuff is more of like something you need in order to make new state machines viable. So the idea of Substrate and the idea of Polkadot is to sort of take away that concern of the consensus layer and bring the state machine layer to the devs. So quick recap of how Polkadot works. We have the relay chain. The relay chain is actually something that we're building with Substrate. It's the main chain of Polkadot. And we have a bunch of parachains which are attached to the relay chain. They're pinned to the relay chain. And they all advance in parallel, which is why we call them parachains, parallelizable chains. You have these actors on the relay chain who are called validators, and their job is to basically sign off on state transitions of the parachains. So, somebody called a collator for the parachain is submitting a state transition saying, this block changes the state of my parachain from A to B. And validators are going to check that. They're going to say, okay, that seems fine. Then they're going to sign off on it, and this opens them up to the risk of slashing. So they don't want to do that for something that they're not going to be actually attesting to. And that's essentially the process of how you advance a relay chain, a parachain. Most of the computation actually happens on the parachains, right? We're not opening up things like smart contracts and all of that jazz on the relay chain itself. It's really just a core layer for those parachains to advance their own state machines, and also for them to communicate amongst each other. And we also have, the idea of a bridge from the perspective of The relay chain, a bridge, kind of just operates as a normal parachain. It just happens to be also tracking the status of some remote parachain or blockchain. So I'll dive a bit deeper into what makes up a parachain. I've got the Vitruvian man up here. He knows a lot about anatomy, so this should be helpful. The main thing is this validation function, and if you just saw Sergey's talk, you already got a bit of a primer on this, but it's basically it's a piece of WebAssembly code that validators all can agree on because it's pegged into the state of the relay chain, right? So everybody knows what the validation function code for parachain X is. They are deterministic, being WebAssembly, and they are self-contained, right? They don't reference anything else on the internet. It's just completely self-contained. And the main export that this validation function blob exports is this function validate. And this is a bit of like Rust code for how that would look. In principle, that's a WebAssembly interface. But you're passing essentially the last header data of the parachain. So, what was the last block? Some information about the state of the Polkadot relay chain. So for instance, the message processing watermarks of other parachains, things like that. And you've got the block data, which is something that is very, very integral to the design of Cumulus, is actually producing this block data. So the idea is you pass in all of these parameters, from the perspective of Polkadot. The last header and the block data are just bags of bytes, right? They don't enforce any kind of internal structure on it. Those are just bytes. And what you get back is either a result, which is you get either something that's okay. The validation function says, yes, this header, this block data, that represents a valid state transition, and you get back a new header of the parachain. And the other option is you can get back an error. So the validation function says, no, this isn't good, this is garbage. And as a validator, you would never sign off on that. Yeah. So the kind of interesting thing is because all of the header data is actually registered on the relay chain. So what the relay chain tracks for every parachain is the header data, the most recent header data of that parachain, and the validation function of that parachain. You can actually follow, at least as a light client, the consensus of a parachain just by looking at the relay chain. And this is why I wanted to make that distinction of safety versus liveness earlier, because you can acquire safety for a parachain just from Polkadot, right? What you need on the other side of things is liveness, the block authorship, and that's what collator nodes are for. So the collator nodes of a parachain are sort of very specific to that parachain, and they actually know how to author blocks. And in particular, what they do is when you look at this block data parameter, this is like a proof that some state transition is valid. And collator nodes, from the perspective of Polkadot, are those nodes who know how to create the proof such that the validation function will return successfully. So in practice, what does that mean? You've definitely got a block, like the actual transactions as part of that proof. There's a lot of flexibility for future research and things that you can do. For instance, that could be like a zero knowledge proof or some kind of succinct proof where all you have to do is check some mathematical constraints, and you can see, okay, that represents a valid state transition because of this fancy succinct proving technique. What we're actually doing is essentially bundling up subsections of the state and passing that along with the block body as the block data. So parachains are pretty simple, I think, to reason about, but just like all blockchains, they're actually really hard to implement, and there's a lot that goes into implementing a parachain in particular that you don't have to deal with when you're implementing a regular blockchain. One of those things is writing the collator node and actually building those block proofs, talking to validators of the relay chain, storing old messages, fetching messages that are incoming from the collators of other parachains, things like that. But the interesting thing is that like you don't have to reduplicate this work, right? Like this is code that's going to be relatively common amongst all parachains. So the idea is to sort of put that into a library, or part of the set of libraries that we're calling Cumulus, and then everybody can just make use of that. So this is a bit of like some of the things that you have to do in general when you're writing a blockchain, like peer discovery, chain synchronization, which for Cumulus in particular is kind of an interesting problem. You've got RPCs, there's optimization, light client protocols, all of that stuff. So that's just a couple of the things that you have to do when you're writing a blockchain. There's actually a lot more than that. So I mean, this is why we built Substrate, basically. And what I want to dive a bit deeper into now is the framework that we have for writing pluggable consensus engines. And also the composable runtime modules. But I think for now the pluggable consensus stuff is probably the most relevant to the talk. So Substrate doesn't make any assumptions about how or when blocks will be produced or finalized. So that actually introduces a lot of more complicated engineering constraints. Like for instance, let's say you're assuming that you have instant finality. Like as soon as a block is produced, it's finalized. That has huge implications with respect to the database layer, for instance. You don't have to store, you can actually index every number or every block just by its number, because you'll never have two blocks that have the same number. As soon as you have non-instant finality, you have to write a database layer that can account for forks and reorganizations and say there could be two block ones. Then you also have to make things sort of deal with the idea of a fork choice rule, right? So you have multiple competing forks. How do you choose one? How do you choose one out of the blocks that are on disk? And how do you choose a chain out of those chains which are being advertised to you on the network? So as soon as you start to remove these assumptions about how blocks are going to be produced or when they're going to be produced and finalized, you're introducing a lot more complexity. But we've spent a lot of time on the early stages of Substrate to actually make sure that all of this is in place, and that gives us a ton of power, because you can actually view Substrate as really fulfilling this duality of state machine and consensus, which is you have like all the code that deals with runtimes and writing runtimes, executing them, and then like you can write all kinds of different consensus modules that provide agreement on them, and we really stick to this this duality. So some of the pieces of the Substrate consensus, pluggable consensus stuff. So this is fundamentally different than what we did. The first time as a team that we really tried to play around with pluggable consensus stuff was in Parity Ethereum. And what we've gone with in Substrate is pretty radically different from that. So we have like a sort of multi-trait system where if you want to build a consensus engine, you're essentially building a few particular components. So one of those is the import queue. So what this essentially does is this abstracts over potentially parallel, potentially out of order verification of incoming blocks. So when you're doing a synchronization, you have to do that very quickly. You might have like 1 million blocks queued, or at least you might have several millions of blocks left to sync. You might be queuing tens of thousands or so. And what you don't want to do is end up in a synchronous loop where you import a block, then do pre-verification, and then import the next one. Because there are certain verification steps that you simply do not need to have execution of the parent for. So that's sort of what the idea of the import queue is. This is going to look radically different for different consensus engines, especially those which are doing any kind of proof of stake consensus. We also have this block import thing, which is that piece of logic for when you are importing a block whose parent has already been imported. So that's where you'll do your like atomic state updates, check for validator set changes, and things like that. And I marked these two with onions because they are onions. And they essentially, you can have composable consensus engines. So, like for instance, for Babe and Grandpa, what we're using on the Kusama network, you have an import queue for Grandpa wrapping an import queue for Babe, and you have a block import for Grandpa wrapping a block import for Babe. And then actually on the Polkadot code base, we have even sort of one step further because you have all the parachains stuff that you need to verify as well, like making sure that there are enough attestations in blocks and things like that. And that's wrapping the Grandpa block import and import queue. So you have several different layers. It's designed to be composable, so you can sort of just stack consensus engines on top of each other, as long as they don't try to do the same thing and interfere with each other, which is something you'll have to figure out at sort of setup time. You know, for instance, Grandpa is a finality gadget and Babe is not. That's, you know, it works. So then the other thing that we have is this idea of a background worker. So the background worker is where like any kind of networking and logic and whatever actually happens. So Grandpa, for instance, this is where the Grandpa voter lives. In the Babe or Aura block authorship systems, this is where the block authorship is actually happening. You have some kind of loop, or you're listening to import notifications and deciding, okay, this slot belongs to me, I'm gonna author a block and then feed it into the block import. And those are further down the line calling the import block and finalized block stuff. So what we've done for Cumulus is basically write a bunch of these components. So in particular, a background worker, which is customized to the idea of being a Polkadot parachain. So what it's doing is essentially it's keeping track of when its turn is going to be to author a new parachain block as a collator, and then authoring that block and then feeding it into a networking process. So, you know, you don't have to import something directly from the background worker into the block import stuff. You can import background worker stuff into, you know, anywhere. We don't really worry too much about exactly how that's supposed to operate. It is a background worker after all. So what you're doing in Cumulus is essentially background worker is authoring a block proposal, sending that over to validators, and then validators are going to run consensus on it, and you're going to download that block from the network contained within a Polkadot block. So yeah, that's the rough design. So I mentioned before that what you actually need in order to observe safety of a parachain is to observe safety of the relay chain so if you observe safety as in consensus of a relay chain block, where that relay chain block contains a parachain header, you have observed safety and consensus on your parachain as well. And this is kind of the only way to do it, in fact. So that means that every node in Cumulus is actually two nodes. It's a node of your parachain, but it's also a node of Polkadot. So it's synchronizing, at the very least as a light client, the Polkadot network so that it can follow the consensus of the Polkadot network. And then it's using that information to know exactly which blocks to download of the parachain. And that's the parachain full node side of things. So I'd like to go into a couple of differences that might sort of illuminate the situation of how parachains are different than sovereign chain Substrate. So in a parachain, finality and consensus are coming from the relay chain, and block authorship depends on information that's derived from the relay chain. So in particular, if we look at that validation function from before, we had that Polkadot status or Polkadot info parameter, which is going to tell us about sort of the states of other parachains or of you know, how message queues are, or you know, perhaps at least just the state root that we can use to prove anything about the Polkadot state. Whereas with a sovereign chain, finality and consensus is all sort of just determined by the nodes of that parachain. And this actually has very broad implications for how, for instance, synchronization algorithms should look compared with parachains versus sovereign chains. And also, the block authorship for a sovereign chain doesn't depend on any other chain. Right, so how do we actually generate this block data parameter in Cumulus? So a lot of what we've done so far in Cumulus has actually happened in the Substrate codebase, and it's particularly for making this feature possible. So this validation function is actually pretty similar to the typical Substrate runtime's execute block function. So the execute block function is taking a block, and it has various externalities attached to it. Queries that the runtime can make, asking the wrapping node about what the state of the system is. So, for instance, what's the storage value at this key, or does this signature verify, and things like that. So the main difference that we have with the validate function is this block data, right? When a validator is executing a validation function, it doesn't have all of the state that it needs to implement those same queries of, what was the state at this key for the parachain that it's validating, all of that stuff. So what we have to do is, in order to wrap a runtime into a validation function, we're essentially wrapping a runtime into another piece of WebAssembly, which is sandboxing that runtime and providing it all of those externalities. So the runtime perceives itself as being within a Substrate environment, but actually it's within a simulated Substrate environment that's running within a Polkadot environment. And the Polkadot environment doesn't have all of the same APIs that a Substrate environment might. And the way that you emulate those Substrate APIs is by drawing out of this block data. So in particular for storage functions. We store all state data in a tree. It's a Merkle tree, it's a hash tree. So you have a root hash at the top, which is referencing some children nodes by hash, which is referencing, and so on, right? And you can traverse the path in the tree and figure out what the value of any particular key is as a key value database. So when I execute a transaction or an extrinsic on Substrate, or any piece of logic on Substrate, what I'm doing is I'm going to be accessing a bunch of different storage values from this tree. So, if we have one transaction, so transaction A, which is accessing this piece of storage, and then we have another transaction in that same block that accesses those pieces of storage, then the entirety of the storage set that we need in order to execute this state transition is shown by this subset of the tree. Excuse me. Yeah. So what collator nodes are doing is essentially executing the block, but executing in a special way where they figure out exactly which nodes of the state tree they need in order to give somebody all of the data that they need in order to re-execute that block. So that's re-executing initialization of the block, execution of extrinsics and inherents, and of closing the block, as in computing the new state root of the block, because this is exactly what a validator needs to be able to do in order to say that a state transition is valid. They're saying that the state root of the tree of the parachain went from A to B, and that's exactly the data that you need. So Cumulus Collator is this block authorship pipeline that does exactly that. There's sort of a special way that you can wrap your runtime. So the collator has both versions of the runtime. It has the runtime as a Substrate node would perceive it, and it also has the validation function as Polkadot would perceive it. And these are essentially the same piece of code. It's just that the Polkadot version has wrapped it and knows how to provide some of those APIs out of parameters, out of storage proofs that have been passed. So one observation is also that if since messages are passed into the validation function, incoming messages to a parachain, you don't necessarily need to re-include them in the block data that's being passed over. That's mostly because it would be redundant. So that's a mild optimization that we can do in the future. So this is sort of a diagram of what that whole system looks like. So we've got the Polkadot collator library, which is sort of a generalization of all collators. This is actually the background worker. So this background worker is hooked into some interface implementation, which Polkadot collator, all it ever does is ask the Cumulus collator, hey, make me a new parachain block and a proof. Cumulus collator will talk to the basic authorship proposer, block proposer, something like that you've hooked into your system. Usually you would use basic authorship. If you're doing something fancier, you can use that. And the basic authorship thing will talk to the runtime. Cumulus collator will use this to generate a proof, feed that back to Polkadot collator, and Polkadot collator will feed that to the Polkadot network, as in the validators who might be revalidating that block. Polkadot collator also talks to the Polkadot network to figure out things like what are the incoming messages that are being sent to this parachain. So what Cumulus is intended to give you is a consensus and chain synchronization algorithm for Substrate that follows a relay chain. So we actually want to do some kind of cool stuff with the chain synchronization algorithm. So, oh, thank you. I really needed that. Thank you. Yeah, winter. So like I mentioned before, let's say you're trying to build a parachain full node, right? So the first thing that you can do is look at the relay chain and see what's the latest finalized parachain block. But if you're a full node, you want to execute all of the blocks in order, or at least build up that full state somehow. So the full state of that block, you want to execute. You want to generate that by executing all of the blocks in order. This kind of differs from a traditional chain synchronization algorithm, because what you will do in a chain synchronization algorithm usually is you don't know the endpoint. There is some abstract endpoint that's growing. You just sync forwards. When you're synchronizing a parachain, you know the endpoint that you're supposed to end up on. So you have a couple options. One is that since it's a blockchain, you can synchronize all the blocks backwards and then walk it forward. But that means that you have to download a lot of data before you can even start executing the chain. The other option is you can just sort of sync forward blindly and hope you reach that same endpoint. But there's not really a great way, without some of the things I'm about to talk about, to do that, right? To know that when I'm looking at block 1000, that this really is the block 1000 that's referenced by block 10 million that's referenced in the Polkadot relay chain. Because you only have one parent hash, right? Block 10 million points to block 9,999,999. It doesn't tell you what block 1000 is going to be. So we can essentially use a piece of technology called Merkle mountain ranges. So this is like how Fly client works, for instance. So the idea is that you can actually create sort of a system of Merkle trees which can be appended to, like if you want to know the canonical hash of any block number according to some ancestry list, you can get a proof out of a Merkle mountain range that will tell you this. But the cool thing about a Merkle mountain range is that you only need like the tops of the trees, the tips of the mountains, in order to add new numbers to this. So this is actually something that you can implement within a runtime without having to store 10 million entries in the state. You only have to store like log 2 of 10 million entries. So log 2 roots for all the tips of the mountain ranges. So that's one of the things that we want to do for the synchronization algorithm. The other thing that Cumulus is giving you is a collator node for producing parachain blocks. Like the idea basically is that you can just take your runtime, feed it into this sort of like wrapping system. You don't have to write any of the collator node stuff yourself, and you'll just have like a full node, a light node, and a collator node for your parachain, if that's what you're trying to write. And also some tools for writing Substrate runtimes that send and receive messages from other parachains. So those would be the runtime modules of Cumulus. It is in the very early stages of development. What we are going to do is like a little bit of a workshop after lunch where we're going to go into showing off like how to deploy a relay chain, like a local relay chain, how to deploy like a Cumulus node with pre-built runtime and connect it to that relay chain, and actually show you that the collator is submitting proofs to the validators and that the parachain is actually growing. But for now, like that's pretty much all you can do with it. Like a lot of the more fancy scripts for like the bring your own runtime, bring your own relay chain stuff are still in the works. So that should be coming fairly soon though. Yeah, so the near-term improvements that we're looking into is like better collator to validator networking and cumulus synchronization, as well as getting the APIs for those runtime modules of how cross-chain message passing should look, so that like you can already, especially if you have a local relay chain where you can ensure the topology of the network, like so that collators are definitely connected to the right validators and so on, that you could already start to do some cross-chain message passing experimentation. A lot of the more complex parts of cross-chain message passing as a feature in general have to do with discovery, traversing the topology when you're dealing with like a full global scale decentralized network and finding the validators, making sure that they're not over flooded, things like that. But if you're just doing this like on your local dev setup, you don't have to really worry about that. So that should be coming as well. Yeah, so that's pretty much it. I guess I have time for questions. Thank you very much.
Hi, I'm John. I have two questions. One is, how are these collator nodes elected? Like it's random elected, or there's an algorithm about that?
Yeah, it's a really good question. So from the perspective of Polkadot, we're actually dealing with unbounded collator sets. So theoretically, from Polkadot's perspective, anybody can be a collator. So we kind of leave this up to the parachain. So what the parachain can say is, the parachain can then limit the set of collators. So it's up to the parachain. So the parachain can say, we're going to have this staking system, and only the top n stakers are allowed to become collators, right? Or you could do something like a proof of work collation parachain, where it's like, as long as somebody has submitted enough proof of work, they're allowed to be a collator of the next block. We try to keep this abstract for Polkadot because we don't want to enforce collator selection mechanisms onto parachains.
So in this case, like if I have a proof of stake chain, then I mean developer needs to specify which slot the following collator are going to be. Like they need to specify the order of the collator themselves.
Yes. This is the kind of runtime module that we would like to include with Cumulus, basically. So to go through a little bit like the architecture of Substrate's like staking system and session keys system, Substrate has a staking module where you can stake, you can nominate, all of that stuff. I'm sure many of you are writing your own proof of stake systems as well. We also have this session keys module, which is independent from the staking module. It has to do with like going from a stash account to a session key, which is like a particular key that's used for a particular task at a particular point in time. The session key module can then plug into any particular kind of consensus module. So it says, okay, we've got this validator set of this key type, and now we're going to plug this into a consensus module that dictates ordering and does initialization, finalization, checks, things like that. The point of all of this being is we can write a module for like collator ordering and collator selection, which is agnostic as to how that validator set is chosen, right? So that's the kind of module that we would like to include in Cumulus, which is, we're not going to make assumptions about how the validator set is chosen, how they set their keys, whether those are their primary keys or simply session keys, but just simply from some kind of predetermined elsewhere in the runtime key set, go to things like collator slot assignment.
Okay, so the second question is, how is the message going to be interchanged between the two parachain? I mean, like at least there are two policies. One is to upload all of the message to the relay chain, then another collator can read the whole message. Another one is just publish the hash, and then the collator do the direct communications or any other.
Yeah, so we're going more in the direction of the second route. So a couple, I think Gavin is planning to talk about this as well. Like this is something that can have like its entirely own presentation, but we're going more in the direction of pinning cryptographic roots, hashes, things like that on the relay chain, so that you can always check that you have gotten the right messages, and then collators using that information on the relay chain to know which information they need from other parachains to figure out what those messages are going to be, then discovering collators or validators from those other parachains and asking them for that information, and then constructing a message packet out of that and feeding it in. So this is all sort of checkable by the Polkadot block execution function. So once you've got the data, you're good to go. The challenges are mostly in acquiring that data once you have the hashes on the relay chain.
Thank you very much.
Yep.
Okay. Unfortunately, we've got to go to lunch, but Rob is going to have a workshop, so we can do questions at the workshop. That's going to be at 2 p.m. in the workshop room. And thank you so much, Rob.
Thank you, everyone.